This square of foil is about to take off on a tiny trip. Don't blink, or you might miss it. That movement was powered entirely by light, a phenomenon called photophoretic flight.
Most people have studied photophoresis in the context of this little physics toy here. This is called a Crookes radiometer. It was invented by William Crookes in the late 1800s. And what's neat about this is it's a series of vanes in a low pressure bulb. And when you shine light on the vanes, they actually start to rotate.
Crookes' radiometer and the free-flying foil both work using the same process, thermal transpiration.
Photophoresis literally means like light-driven motion, and thermal transpiration is one kind of that. Thermal transpiration describes the flow of gas at low pressures from a region that is cold to a region that is hot. And typically that's a little counterintuitive, right? We're used to thinking of things moving from hot to cold. But when you're at low pressures, things get a little wonky.
In the radiometer, this temperature difference is created by coating one side of a vane with black paint that absorbs radiation and warms up, and the other with a reflective material that stays cool. The new device achieves a similar effect with a pair of nanofabricated membranes.
The top membrane, when illuminated, stays cool, but the bottom membrane stays hot. And the way that we do that is we coat the bottom membrane with a layer of chromium, which is very absorptive to things like sunlight. So when you shine light on the structure, the bottom heats up, the top stays cool, and that causes this airflow both around the sides of the structure and through these perforations in the membranes that causes the entire structure to lift up.
And the device can generate lift with around half the intensity of full sunlight, at 55% of what's called the solar constant. Ben and his colleagues then used computer modelling to design a larger circular version of the device, capable of carrying small loads in the mesosphere, the region of Earth's atmosphere where the air is too thin for most forms of flight.
It's quite convenient that these devices like to fly in a region of the atmosphere that not much else can, because it kind of bridges a gap between lower altitude hardware like planes and balloons and things that are in orbit like satellites. Because not much else can fly in this region of the atmosphere, our devices could be used to collect really important weather and climate data and help us learn more about how the atmosphere changes over time. So you could collect things like wind, pressure, temperature data. All of that is important to climate modeling.
And the device could even work in other low-pressure atmospheres. For example, on Mars.
So we did some modeling of how well these things would fly on Mars, and it turns out that they would have pretty comparable performance to how they would act on Earth. And so you could do the same applications in the Martian atmosphere. And because these devices are so lightweight, it wouldn't be terribly costly to send a rocket with these devices out to Mars. And obviously that's kind of a blue sky idea way down the line, but the physics says it works.
There is still work to be done to take this tiny fluttering surface from the lab to the mesosphere, but this team have high hopes about the possible applications of this former Victorian curiosity.
I think it's just cool that we've taken this kind of obscure piece of physics and actually translated it to real-world use, especially in such a pressing time for climate and atmospheric science. Being able to use these as tools to collect data that we previously couldn't is really exciting to me.